Archive started.
Hello, this is Dr. Leslie Ann Asmus, and I'm going to be kicking off the first of a number of different recordings related to discrete random variables and the probability distributions. So to kick that off, we asked the question of what is a random variable? And most of the experiments that we've talked about so far, actually, in the last section regarding general probability concepts, we looked at sample space and the fact that you can have, in the sample space would be all possible outcomes. We looked at events and giving a description to a particular outcome or a group of outcomes that have that shared characteristic. And so here what we're going to be doing is saying, okay, we're going to define an experiment and we're going to do a mapping of outcomes to something called a random variable, numerical outcomes whose value change from experiment to experiment, and we're going to call that a random variable. So if we were to do an experiment in one particular elementary school and take the heights of all the children in that school, we would expect those random variables, the values that are possible to be different for different kids. And then likewise, if we went to a different public school or a different elementary school and did the same thing and have different possible values for that random variables. And these give you some examples. Numbers of voters favoring various candidates, tensile strength of wires, number of accidents at specified intersections. So those are kind of general ideas, and we're going to look at different kinds of random variables, discrete ones being those. Let me actually continue on, but those would be the ones that say, well, especially if you think about accidents happening in an intersection. Let's say for a 2-hour 2-hour block of time, you would say that there could be 0 accidents, 1 accident, 2 accidents, 3 accidents. It'd be pretty drastic, but yeah, I suppose you could have 10 accidents in that same intersection over a 2-hour window. Not your best intersection then to go to. But these are some examples of random variables. Here's another one. A section of electrical circuit has 2 relays, numbered 1 and 2, operating in parallel. The current will flow when a switch is thrown if either one or both of the relays close. The probability that a relay will close properly is 0.8, and this probability is the same for each relay. The relays are operate independently, we assume. Let E1 and E2 denote the events that relay 1 and 2 close properly when the switch is thrown. So E1 associated with the first relay and E2 being the second relay, and that they're closing properly. So the probability of E1 that the first relay closes properly is 0.8. Probability of the second relay closing properly is 0.8 also. When a switch is thrown, the numerical outcome of some interest to the operator of this system is X, the number of relays that close properly. X, then, is a random variable, and it can take only 3 possible values. 0, which would map to both relays fail, essentially. 1, which means one of the 2 relays close properly. Or 2, which would indicate that both relays have closed properly. So, what are the probabilities for each of these? I'll leave that as an exercise to you. Keep in mind that they're independent. So go back to your notes on the probability and what does independence give us? Okay, so another example of, well, actually, no, how about that? Look at there, you get the bonus here. You're going to get the solution. That E1 and E2 denote the events that relay 1 and 2 close properly when a switch is thrown. So they can take the 3 values, either 0, 1, or 2. Probability of X equals 0. That's our mapping, right? Neither of the relays work. Neither of them close properly. So what's the probability of not E1 and not E2? That, because of independence, is equal to the probability of not E1 times the probability of not E2. And we know that 0.8 was the probability that they both that they close, each one of them individually. And so therefore, 0.2 is the probability that E1 won't close properly, times probability E2 fails also. And so we get 0.2 times 0.2 is 0.04. What's the probability that one of them closes properly? And that is the probability that E1 closes properly and E2 does not close properly. Or probability that E1 doesn't close properly and E2 does close properly. And so what's the probability? That's equal to the probability of, and we know this again from our addition, our union, and they are mutually exclusive. So we have the probability of E1 closing, so it's just the sum of those two probabilities. And so there we have, by the independence, we again have the probability of E1 closing is going to be 0.8 times the probability of E2 not closing correctly, which is 0.2. But now we also have to add that to the probability that E1 fails and E2 succeeds. So therefore we have a total probability that the random variable that x equal 1, suggesting that one of the relays closed properly, is equal to 0.32. Probability x is equal to 2. That tells us that both relays closed properly. That's the probability that E1 closes and the intersection E2 closes properly. And by independence, we again have probability E1 times the probability E2. And by the definition, we have 0.8 times 0.8 is equal to 0.64. Now, if we wanted to find out what's the probability that at least one of them works, right? Then that might be of some interest, because if there at least one might mean that overall the system's going to work okay. So then you would look and say, well, what's the probability of E1, x is equal to 1 or 2? That is equal to probability x is equal to 1 plus the probability x equal 2. So now we know, since above we solved for those two probabilities, we have a 0.96 chance that the current will flow. And we note also this is just another way of looking and saying, okay, for random variables, this particular example, it can take 3 possible values. The sum of those probabilities is equal to 1.0. And that again goes back to what we were talking about in the previous section about basic probability concepts, that the sum of all probabilities for outcomes in the sample space, they must always equal to 1.0, the sum of that. So that's what we're looking at here. So random variables defined. Definition: a random variable is a mathematical function that associates a number with every possible outcome in the sample space S. That's what we just looked at. Sample space S had one relay working, no relays working, both relays working. So those were our 3 different outcomes possible. And so we could define a random variable that was reflective of those 3 possible outcomes. Let's see, capital letters, usually X or Y, sometimes you'll see Z as random variables, used to denote the random variables. Capital letters indicating the random variables, lowercase indicating, and we'll see this in the mathematical notation, the lowercase are typically to indicate that a particular random variable X or Y, we're looking at it mathematically speaking, equal to lowercase x or y particular values. So a discrete random variable is a random variable that can take on or assume finite number of possible values, x1, x2, xk. Again, we're looking at integer values, and so we'll be working in that realm. So you imagine back to the intersection, and the intersection with accidents. You can have 0 accidents, 1 accident, 2 accidents, but you can't have 1.5 accidents. Think about the manufacturing environment. So you're making, let's say, semiconductor chips, and you're counting how many, what's the probability of 3 chips being functioning properly, 4 chips functioning, being manufactured properly, and so forth like this. You don't have 0.5 of a semiconductor chip coming off the manufacturing line working properly. So that would be discrete. We're going to call those discrete random variables. Random variable is said to be discrete if it can only take a finite number and account or countably infinite of possible values of x. So again, going back to our probability rules, something similar here, we're going to work now with random variables. Probability of your random variable x taking any particular value, that probability must be greater than or equal to 0. So what's the probability of neither of the relays working? Had to be a positive or at least non-zero probability. We can have a negative probability. And again, we looked at the sum of those across all the outcomes possible in the sample space. Those probabilities added up to 1. This is what's termed the probability distribution of a random variable x. The function p of x is called the probability distribution of a random variable x. So as a class example for this, among 10 applicants for an open position, 6 are women, 4 are men. Suppose that 3 applicants are randomly selected from the applicant pool for final interviews. Find the probability distribution for x, the number of female applicants among the final 3. So this is kind of similar to what we looked at previously, a little bit more complicated. Okay, so what's the probability that x is equal to 0? Again, if x is the number of females among the final 3, x, the random variable, takes a value of 0 when all 3 of the finalists are men. X is equal to 1 female, 2 males in the final 3. X is equal to 2, 1 male, 2 females. Again, the focus is on how many females are in the final 3. So there could be 0 females, 1 female, 2 females, and then finally you could have x is equal to 3, the random variable, 3 females in the final 3. So how do you figure out the probabilities of that? And this is a blend of, we're looking at, okay, so how many ways can you, out of the 4 men, in the first case we're looking at probability x is equal to 0, meaning no females. So how many ways can we pick 3 men out of the 4 men that are there? That's 4, choose 3. Again, we don't care about order, we just care about 3 of those guys. 3 of the men are picked. And how many different ways can you pick 0 women out of the 6 women that you have in the candidate pool? And that's 6, choose 0. And of course, there's only one way to pick that, to do that. We have the product rule. N1 times N2, so the number, that goes back to our product rule for a number of ways that you can have N1 followed by number of ways that you can have N2. So N1 times N2, that's our product rule there. Okay, so that gives us our event then, right, that we're of interest to us is the event of how many females in the final 3. So what's the probability of our event A? In this case, 0 females. That's the top part. And then we put that over the total number of ways that you could pick 3 candidates from the 10 that are in the pool. That's 10, choose 3. So NA over N of what we had in the previous sessions on probability. So in total, that turns out to be 1/30th. And we do the same kind of logic for the probability of random variable x equal 1 female in the final 3. So 1 female, 2 males. Similar kind of logic. How many different ways can you pick 2 males out of the 4 men that you have? Times how many ways can you pick 1 female out of the 6 women that you have? And of course, there's 6 different women. You can pick, and you're picking one of those. So there's 6 different ways you could do. 6 choose 1 is 6. And then again, so that's your N sub A, so to speak. Your event N is A, and that event would be described as 1 female and 2 males, picked in 3. And you put that over the number of ways that you can pick 3 people from 10 in your pool. So that probability works out to be 3 over 10. Finally, you do the same logic there. 4 choose 1 because you're looking for 1 male now. There's 4 men to pick from times